That's just required to have a game. Okay, so the only things that can still change and have interesting games is deterministic versus chance-oriented, perfect versus imperfect information. And see, here are some of the examples. So deterministic with perfect information are games like chess, checkers, Go, and Othello. Okay, and that's the one that we made fast progress on. Actually, in fact, everything in this except Go was actually solved even 2 years back. And then Go also got solved. Solved in the sense that we are better than humans. By the way, I should make this distinction between game being solved versus game is out of human reach. Do you understand what I'm saying? Okay. When we chess, how many of you think chess is solved? How many of you think chess is solved? Okay. Chess is not solved. Solved essentially means given a board position, there is a theorem saying, you will win or lose. Or given a board position and your move, your intended move, it tells you that irrespective of what happens, you will win, you will lose, or you will be wrong. That's a theorem. What happened actually in chess is that we just are better than humans. That's all. Okay, solve is a much harder goal than crushing humans. Okay, so for example, the problem of lifting everything, has this been solved or not? No. But do people compete with machines in trying to lift stuff? That ship has sailed long back. Right? I mean, if you haven't seen the huge cranes in front of the BYEC, which are basically taking almost small-sized houses and lifting them and putting on the 17th floor. We don't any longer, compete with machines. Machines have won that game without actually lifting everything in the universe. That's not possible. Okay? So it's important to know that none of these games are actually solved. Actually, it turns out, okay, so if you want to know what is a game that is solved, tic-tac-toe. Tic-tac-toe is solved. If you're still playing tic-tac-toe, or if your nephews and nieces are still playing tic-tac-toe, tell them this information. That, it's just you're wasting your time. It's solved. Okay. Whereas chess is not solved, Go is not solved. I think, in fact, one of either checkers or Othello are close to being solved. Not Go. Either checkers or Othello are being close to being solved. Go is nowhere near being solved. But in fact, big games, saying solved means you need to have theorems. That's not possible. And by the way, this is also an interesting thing to realize that sometimes you can make huge progress in games but not make as good a progress in single-agent problems. For example, the best you could do in deterministic single-agent search for tile puzzles, optimal solution for tile puzzles, the state of the art is 36 tile puzzle. So you guys can do 15 in your projects. The state of the art is pretty much 36. Squares beyond that, you can't actually do optimal solution in any reasonable time. Okay. However, on the other hand, most of us think, oh, that's such a loser kind of a thing to do. Who cares about M puzzle games? Whereas Go and chess, wow, machines are winning. But the reality is the goalpost has changed. In one case, the goalpost is optimal. It's not. We never asked, can you do better than humans in solving the 8 puzzle problem? Most humans think 8 puzzle problem and 15 puzzle problem are so boring that they would refuse to even do them. Do you see what I'm saying? But we're just asking, can you find a probably optimal solution for any given initial configuration to goal configuration? That's a much harder guarantee than can you crush the mere mortals. And crushing the mere mortals, it turns out, is what games try to do. And actually progress there is It's a different kind of a thing. It's like if we become smarter, which is unlikely because evolution we seem to have reached some reasonable plateau, evolutionarily speaking. If we become smarter and smarter, then the machines have to keep up. But we are pretty much a certain level of smartness, and machines can easily do well in narrow areas better than us. Okay, so that's useful to remember. Anyway, perfect, and in terms of chance games with chance, things like backgammon and Monopoly are games with chance. Typically, any game where you will have dice that you have to throw, that's basically you want to take, snakes and ladders. Won't it be a beautiful game if it was deterministic? Right? I mean, I'll just go like this. As long as I have eyes, I just go up and type. It's this chance that kills me because everybody knows that they're supposed to take the ladder. But when they throw the die basically says, no, sorry, you're going to be beaten by the snake. That's it. I mean, you're done. Right? So again, so silly games can become interesting if you add chance to them. So deterministic games have to be, they're basically to be interesting, they have to be much harder. Okay. Now, imperfect information essentially is you don't even know what's on the board, what's the game. Okay, and in fact, there are actually crazy people in the world who play this game called Kriegspiel, which is blindfolded chess. As if chess isn't hard enough, you just actually, basically both the players essentially play blindfolded chess. So neither of them know the board position. And they still have to make moves. And there would be an oracle in the middle, not Larry Ellison, but a normal oracle. In computer science, oracle is not Larry Ellison, the oracle guy, but something which knows more information about the problem and can answer some questions. So the oracle can be asked, can I do this move? And if in fact you're trying to move into a square where there is already a pawn, and I actually mentioned this in respect to one of the questions on the other side. If you're trying to move into in normal chess, unless you're kind of drunk, you won't try to move into a square that was already occupied. A cell that's occupied by one of the pawns or something, unless you're trying to kill that pawn. You can't just say, scoot a little bit, I can also stand. That's not allowed. Right? It's not allowed. Right? Whereas, if you don't know, if you're not keeping track, actually the entire game is, it's not seen. And remember, in the beginning, of course, they know how the game is. But then they don't also see what the other guy's move is. They only know what their move is. So they might very well try to get into a cell, and the oracle says, sorry guys, you can't do that. Find something else to do. And the question is, with that kind of information, can you win the game? And even more interesting question is, who are these crazy people who want to play such games? Okay, but there are people like that. And so imperfect information, and then, but in chess, it is still deterministic. By the way, this is a beautiful slide because it sort of makes you think about the real difference between dynamic versus stochastic, which is no longer in this slide because all games are supposed to be dynamic. And deterministic versus, dynamic versus static, which is no longer in this slide, and deterministic versus chance on one side and perfect versus imperfect information. So for example, even though Kriegspiel looks like a crazy game, it is still deterministic. When you make a move, there is a deterministic outcome to that move. Poker, on the other hand, essentially has both imperfect information, that means you don't know what the cards of the other person are, and chance. Because the cards you get as well as the cards your friends get, your opponent gets, are both determined by chance. And while talking about this, you have to realize that I actually don't play most of these games. I don't actually play chess at all. I think it's a humankind's big mistake to equate chess with intelligence. And mostly probably because I can't play chess. But, but the reality is I'm talking about this as a stranger from Mars. But it may mean a lot to you because you guys play all this. Okay. So by the way, nuclear war. Where the heck did that come from? As I say, nobody expects Spanish Inquisition for Spanish. It's already there. Okay. Why did nuclear war come from? We don't play games because we have nothing better to do. we play games because the entire society is game theoretic in some ways. You know where the maximum amount of research for game theory got done? And for what reason? Who knows? Yes.
During the Cold War,
Yes.
tried to simulate nuclear attacks.
Yes. And where? There's a place called Rand Corporation in Santa Monica. Okay. And basically, Uncle Sam put a huge number of bright people there and said, guys, do something to give us technical advantage over Soviet Union. You know, in playing all kinds of games. They weren't just talking about chess, they were also talking about games like Game of Chicken, which is what we are playing right now with North Korea. Okay, so that, you know, basically what is the best strategy? And sometimes the strategies could be mixed strategies. That means it has to have some, you know, probabilistic chance involved in what move you would be making. But a lot of work actually got done in that context. And so not surprisingly, actually nuclear war is, in many ways, is like playing poker. Okay? Anyway. Nixon letters here, right? There are some points there that we can make. So, okay, so what I'm going to do is, I'm assuming that you know how to do this right now. Right? You all figured this out. But since we saw, and so I also, and you all know alphabet pruning already. So we are done right now, right? But since you at least seen alphabet pruning, and some people get bored, being, you know, if I do the whole thing again, because there's a little video that explains this. So I actually showed you the Bobby Fischer video because what I want to do is I want to do this without numbers. Numbers are but a crutch. Just like board and pawn is like a crutch, and so then things that throws the whole board out. It says now think about where the game is going. Okay, so let's call these not numbers. I'll do this this way. X, Y, Z, W, U, V, A, B, C. Okay? Right? If you can do it, I mean your program does it that way, essentially. So let's actually play this game. Let's do it in the XYZs. And then if you understand it at that level, then you understand it really. Okay? So let me just walk you through this. So remember that we are going to be doing depth first search of this. So even though you see this whole thing in front of you, in fact you are playing two roles. One is as an oracle who essentially gives to your program information about, you know, additional pieces of the search tree. And the program itself is just looking at the piece of the gateway that is expanding at this point. So obviously you will start with A. So in the beginning, you will assume that everybody, A, B, C, D, all these things, the capital guys, they all essentially have some bounds as to how well they can do. Okay, so we will put these bounds this way. For max guy, they want to be, the only useful bound is the bound such that they can't do worse than that. So for max, you always think in terms of greater than or equal to bound. For min, you think in terms of less than or equal to bound. Right? So for a greater than or equal to, what can you say before we even started? What can you say is the bound for A? Minus infinity. Right? So this is greater than or equal to minus infinity, and this is less than or equal to plus infinity. That much is for sure. Okay, so you act as if for every min node, there is a plus infinity initialized bound, and every max node, there is a minus infinity initialized bound. Right? Okay, so now you start going forward. So basically you're doing depth first, the normal way. So I go this way, I go this way. At this point, essentially, my oracle, I realize that E is a leaf node because it has no more children. When you try to expand E, your program says, no, it's a leaf node, it's a terminal position. And it tells you that the value of E is x. Now the interesting thing is we thought it will be only less than or equal to plus infinity. It can't drive down the game value for not, below plus infinity. But now it knows that it has a child whose value is x. Right? Which basically means it actually can drive down the value of the game on that branch to at least x. So, unless x also happens to be minus infinity, really, you now instead of being less than or equal to, unless x also happens to be plus infinity, what you really have is previously your bound is less than or equal to plus infinity, but now your bound is your minimum of your old bound and the latest information you got. You see that? Right? So this is minimum of, so what you get here is min of plus infinity and x. Okay, I'll just assume that is x to make things easier. Okay, min of plus infinity x. So right now I will just cut this off and then put x at the bottom. Okay, now basically b is done. So this is less than or equal to x. Now you still, the depth first search is still below b. It is not yet gone up. Okay, so you come back to b and say what is your next child. Next child is f. And its value is y. So it basically takes min of x and y. Right? So the bound now becomes min of x and y. Okay? In the real problem it was min of 4 and 5, which happens to be 4. But if I change the numbers, if this is 4 and this is 3, it will actually be 3. What it really got is min of x and y. Okay? That's it. So now, at this point then the search says, okay, what about your next child? Again, remember that you see this entire tree. Search itself doesn't see the tree. So it got first child, it got second child, then it says, give me the third child. And your program says no more children for B. If there is no more children for B, essentially your bound is your real value. Do you see what I'm saying? Okay, so the moment if you realize that there is no more children for B, basically it actually, instead of min xy, it's not less than or equal to min xy, it's actually equal to min xy. Anytime a node gets its value, its true value, its parent changes their bound. And that's one way of thinking about it, but depth first search does that automatically because it's no longer, it's currently not even thinking about A, it's still under B. And after B is over, it will go back to A and say, give me more of your children. But just before doing that, it can say, let me see if I can change your bound. So the way it will change its bound is min xy is the new bound that is coming from this direction, and it already has a minus infinity bound. It already has a minus infinity bound. Right? Okay? So all I need is to take max of minus infinity and min of xy. Max of minus infinity and min of xy. Unless min of xy itself becomes minus infinity, which is possible, normally you just write min of xy. So at this point I'll cut this and say min of xy. It's greater than or equal to min of xy. Okay? Now I go down here this way, the same way, and then basically I go to C, I go to G, and G gets a Z, and this basically means this is less than or equal to, this is less than or equal to Z first, and then less than or equal to Z, and then you go down here and you get a W. Okay, so remember that after you get less than or equal to z here, then you ask what's the next child. Next child is h, and you know depth first search necessarily goes down below h. Then it finds a w here, and so this is greater than or equal to w. Okay, and then it becomes greater than or equal to max of w and u. And then it just becomes equal to this value. So this guy's value is max of w and u. Now you go back to C. And C basically says it's min now of Z and max of W and U. Okay? So I'll write this is less than or equal to min of C and max of W and U. Okay? At that point you got that, and then you come down this way. Okay, and when you, so at this point again, now when are the bounds? So I'm just, the way I'm doing it right now, I'm only showing you the bounds. The question is, when do you kill search? When do you kill search? At any given point of time, whenever you update the bound, you look up the tree. Look up the tree, and if you are a min node, you look for your max ancestors. And if you're a max node, you look for min ancestors. Okay, so min is trying to keep something below, and if a max guy is already going to keep that above, then you throw, you kill the search. Okay, so in fact, let me write down the condition here. So for example, when you got here, would there be a cutoff here or not? How many people think there will be a cutoff?
Yes.
Right here. Because I basically did this and I did this, and now my bound is less than or equal to min of Z and max of W and V. How many people think there's definitely going to be a cutoff? One. How many people think there definitely won't be a cutoff? How many people think it depends? One place where wishy-washiness actually wins. It of course depends. It depends on X, Y, W and V. Right? Right? So what you need to do is, if in fact min of X, Y is greater than or equal to, I'm sorry, this should not have been min here. It should have been, yeah, the min of X, Y is, this is correct. Min of X, Y is greater than or equal to min of Z and max of W and U. If this is satisfied, there will be a cutoff. What you are doing with actual numbers is you are basically simplifying these expressions right at that point of time, because you have actual numbers. But really what your program is doing is checking these. Okay, so obviously because I'm doing it in X, Y, Z, W, U, E, A, B, C kind of a thing, there won't be any dramatic cutoffs. If you want cutoff, tell me. I mean, I'll say I'll give you cutoff if you can choose your X, Y, Z, W, and U such that this equation is satisfied. This inequality is satisfied. If it is done, I'll give you a cutoff. If not, I can't give you a cutoff. Now, of course, it's not in your hands to change that. It is what it is. Basically, it comes from the. Any questions on what is happening in alpha beta pooling?
I just have one question. Like this backward check is done is every state, right? Whenever we before we go deep, we have to check with the parents also.
Yes, anytime you update a child's bound, then you check for cutoff based on its ancestors. Now, given this, by the way, I asked the following thing. Okay, if I ask you what would be the backup value of A, and I'd allow you to say, you can either say I don't know at all, or you say it will be one of this big set of numbers. will you be able to tell what will be the backup value of 18? It will be just one of these numbers, x, y, z, w, u, v, a, b, c. The big issue is who will win, which one will actually be. So it's like these are all the descendants of this node. One of these descendants actually winds up being the one that decides the right move for A. So because you're doing mins and maxes, the backup value would be one of the lower level values. Okay, yes?
So you said that in the worst case, alpha beta pruning will be 0, right? No pruning.
Yes. That basically means none of these equalities wound up being true. None of these inequalities wound up being true. And so you don't get any extra cutoff.
Is that even possible for
Yes.
a game?
Yes. So, so there is this thing basically that shows the guy called Donald Knuth, whose name, how many of you know Donald Knuth's name? Okay, the rest of you are sort of not in computer science. So Donald Knuth basically, essentially did the original analysis of alpha beta pruning. And you can read this. Essentially what he showed is the best case scenario, if it ever occurs, will look like this. Where all the dotted lines are cut off. And all the solid lines are actually evaluated. And actually there's a pattern. Notice that you have to look at all three here before you get a value here. So you have to look at all three here. Whereas if you are the luckiest person, as soon as you look at one side, the bound cutoff will occur. Do you see what I'm saying? So that's the kind of thing that's happening. Again, when you come here, you have to look at all three here. And then the moment you get all three here, this guy can cut off and so this entire thing can go off. This is the best possible case that you can imagine. And if you do some simple algebra, you'll realize that this best possible case corresponds to the total number of nodes, the ones in dark at the bottom level. The total number of those nodes is b power floor of d by 2 plus b power ceiling of d by 2. Floor, with d is the depth and it's an integer, and so floor and ceiling are. So it's like 2 times b power d by 2, essentially. So instead of doing a search of b power d, you're doing a search of b power d by 2. Now b power d by 2, b power d by 2 can be written as square root of b power d. I'm sorry, it can be written as, square root of b power d. So you are basically, where the other search was doing b power d, you are only doing square root of b power d search. Which essentially means if you had actually enough time to do b power d search, and you are having the best case scenario, you are the luckiest person that day, then you can go twice the depth, because root b power 2 times d would be b power d. So this is why we say in the very best case, alpha beta pruning effectively extends the depth to 2. In the worst case, it doesn't do it. And there really isn't, other than the brain power that you're losing in actually writing your algorithm such that it keeps track of these bounds, there is no increased complexity of the program in terms of the runtime complexity. So alpha beta pruning is one of those things that if you don't do it, it's because you're just intellectually lazy. You see what I'm saying? And there is no good way of saying, I want to be intellectually lazy, please let me be. Okay? So this is just a great idea, and you are supposed to use it. And it's one of these things which tells you that for every problem, you can be clever and realize that certain extra work can be avoided. Okay? One other thing that I want to show, okay, this is just one more example of what we do. I want to show it to you, and then this is my turn. Okay, so the last thing I want to mention again, the last thing basically is essentially that you have resource limits because of which you can't take the tree all the way down. And so essentially for partial nodes that you just go to some depth, and then look at how good that partial node that is, and then you try to have an evaluation function. The evaluation functions in the past used to be of this type. Essentially, for example, the evaluation function for tic-tac-toe, it would say if it's a win for max plus infinity. If it's a lose for max minus infinity. If it's a draw for max, that means you know it's a draw, it's 0. If not, then count the number of rows, columns, diagonals that are still open for max. Subtract from it the number of rows, columns, diagonals that are still open for min. That will tell you how good the position is for max. Now when you are naughty, this is because you kind of know what the game does and you are thinking this is a reasonable heuristic. For chess, coming up with these kinds of evaluation functions are actually hard. Basically, people will talk about things like the piece strength, the board configuration, etc. All of which are syntactic properties of the board that grandmasters decided are important, and then you essentially combine them into some simple heuristic function and use that as an evaluation function. And that's actually what Deep Blue did. And I'll end with this last slide, which is that in the case of Deep Blue, they spent much less time on the evaluation function because there was no good way of doing the evaluation function than asking the experts, what do you think I should be using as the function? And they spent a lot more time on actually doing this alpha beta pruning and the game tree search very efficiently. One of the things that you may not realize is at that time IBM developed an application-specific integrated circuit, a VLSI circuit, whose only purpose is to very quickly generate chess moves so that the tree can be generated very fast. Okay, and that's what they did in '97, and they used more or less a very simple evaluation function. The research basically was on efficiency of search rather than on the how good the evaluation function is, because evaluation function is given by the experts anyway. In AlphaGo, on the other hand, essentially there was only so much you could do in terms of improving search because Go is a much harder game in terms of the size of the search. Its branching factor is significantly higher than that of chess. How many of you know Go? So we are basically Martians talking to Martians about some game. I don't know Go myself, but it's understood that Go has a much higher branching factor, and you can't go anywhere in Go, pun intended, I guess, without actually dealing with a better evaluation function. And so that's where they essentially use a humongous number of stored games that were online and learned evaluation functions from that, and use that evaluation function in a search strategy. It's a slightly different search strategy. It's a variation of min-max search called Monte Carlo search that we will talk later. So that's where game trees basically are right now. Okay, and we will end here. This is going to be your second project, if I remember correctly, because eventually you want that man